Okay, so today we we continue our discussion on a journey that attempts to build the theoretical framework for studying macromolecular systems, so to say, ground up. So for the most fundamental approach, which consists in writing down the equations for the Schrödinger equation for all atoms and all electrons, up to the point where we provide a systematic scheme to simulate the classical dynamics of nuclei. So what we did over the last lectures was, let me review what we did from the conceptual point of view over the last lectures and try to sort of revisit what we did in a hopefully coherent manner, okay? So we started off by saying that we have a complex system, which is, I'm representing here as a blob, which basically is whatever is my solute plus solvent system, where you have a macromolecule, a bunch of water molecules, and it is actually a physical system. You can consider it as, you know, a protein in a glass that you study with some experimental probe, for example. And one way to access this experimentally is by probing and observing. Let's call it O, right? And this observable, since it's a classical quantity, it's just a function of the phase space variable at time t, right? For instance, if it's the temperature, is the average kinetic energy, but it could be the instantaneous distance between two endpoints of a polymer where you have attached some dynes, and then you probe the fluorescent response, the fret signal between the donor and the acceptor, using terminology that some of you who are more into imaging might have familiar with, right? Now, clearly, if I had, you know, infinite resolution, I am a superhuman being, I could visualize each and every molecule in the system, and I could visualize all atoms, and clearly, with this knowledge, this observable, which you are actually measuring, is depending on the specific trajectory that your system is undertaking in that very particular time, right? So if you had infinite time resolution, you would start from an observable, and you would the initial time, and you would see the time evolution of your observables with arbitrary time resolution. This is O, and this is T. Do you agree with me? Now, these specific trajectories would depend on the initial condition of your system, because it's a function of the phase space trajectory, right? And the phase space trajectory is uniquely determined by the initial condition. So if I knew exactly the initial condition at which the time zero the experiment was carried out, I could in principle repeat a theoretical calculation that would yield a trajectory, exactly one trajectory, and I could compare my trajectory with the trajectory observed in the experiment, right? Do you agree? And this would be a completely deterministic endeavor, right? Too bad this cannot be done. Why? Well, for two main reasons. Reason number one, I have no control on the initial conditions on which the experiment was carried out. I don't know the position and velocity of all the atoms and all the water molecules in the protein in the solute, right? So even if I know the equations of motion, I don't know the initial conditions. And since different initial conditions yield different trajectories, I would not be able to compare my trajectory to the trajectory that is measured in the experiment. Right? The second reason this would not be possible is that even the experiment have a finite time resolution. So effectively, what experiments do, they measure running time averages. Because their experiment itself, the data-taking part of the experiment takes a finite time. Right? So here we were presented with a problem. How do we compare theory with experiment? How do we make predictions if A, we don't know the initial condition, B, even experiments do not allow you to perform instantaneous measurements, but only local time averages. So in other words, experiments measure the average of O over a finite time. And we call that time averages. So the problem that we try to address over the first few lectures was the following. How do we make contact with experimentally measurable quantities, starting from the theory, given that we have only partial knowledge of the system and we have no way to go beyond that, because it's completely unrealistic to imagine a scenario in which A, I determine all the Avogadro number of initial conditions that determine my initial condition in my experimental setup. B, even if I did, I needed to do that with infinite accuracy, whatever it means, because of chaotic behavior. And a small change in the initial condition would ultimately result in a very large deviation. So clearly there's no way we can just try to get this out of simulations, right? This is a radically different situation than the situation in which I shoot a cannonball, I predict the landing position and landing time, and I measure it. Because in that case, I know exactly to very good accuracy the initial condition of my system. I can measure and then compare to my first general physics course predictions. Okay? To tackle this problem, we took the statistical physics way. And the statistical physics way was, let's abandon the concept of trajectory as the focus of our study. We are only able to assess finite regions of phase space, or average over finite region of phase space. We don't know the initial conditions, in other words. So the natural concept is not the concept of individual trajectories, but density in phase space. In other words, all we can do from a theoretical perspective, we use this phase space notation, this is the phase space, is address the following question. We know my initial state is distributed according to some initial distribution in phase space. I don't know exactly the point in phase space I am, but I can assess with reasonable accuracy an initial distribution. Okay? And now I know that from each of these points in phase space there is only one trajectory. And I can ask myself, what is the distribution in phase space at a later time? Right? So the problem now is, what is the phase space distribution gamma of t given gamma of t at t naught, the initial time? Right? So, I want to emphasize that we have started with one problem. We did not answer that problem yet. Instead, we considered a slightly different problem. what is the evolution of phase space distribution. Okay? At the end of this discussion, we will need to make contact between this and that. Okay, to establish a relationship between the upper board, which is where the experiment lives, and the lower board, which is where the theory lives. Do you follow me? Very good. So what we did last lecture was to assume and underline Hamiltonian dynamics and use that assumption of an underlying Hamiltonian dynamics to derive an equation that governs the time evolution of the phase space distribution density. Okay? Which addresses the fundamental question, at least at the formal level, it addresses the fundamental question, what is rho of gamma and t given rho of gamma and t0? And we arrived, after some math, to the Liouville's equation, which I will write here again for your consideration, which is an equation that determines the evolution in time of the phase space density for a Hamiltonian system in terms of an operator called the Liouvillean operator, L, acting on the phase space distribution. The Liouvillean operator has a specific form that defines a partial differential equation. So let me write down the Liouvillean operator for you. The Liouvillean is the sum. Okay. Forgive me, there's a minus sign with this convention. There. Or you can put the minus sign here. Okay? Minus d rho by dt equals L, which establishes basically a continuity equation. But if I write this explicitly, now I'm using all n degrees of freedom. In my previous notes, I was using just 1 degree of freedom. Now we understood the concept, we can write this for all degrees of freedom. Is the sum from 1 to n dh by d r I times, dpi times d by d r I negative dh over d r I times d by d p I. Now, I'm using somewhat weird notations here because I have a partial derivative with respect to a vector, which of course is an abuse of notation. What I should have written is the gradient with respect to the p coordinates inner product with the gradient for each particle. But what I mean by this is that you do this coordinate by coordinate, right? It's clear what I mean notation-wise. It's a common notation you see in papers and in books for this. So rather than writing gradients and Laplacians and divergences, you can use these notations. It simply means coordinate by coordinate for each particle, differentiate for the k, for the first coordinate momentum, and multiply by the first coordinate, the partial derivative with respect to the first coordinate of that particle, and do that for all coordinates and for all particles. Okay? Is this clear mathematically? Okay, so we basically almost stopped there up to some preliminary concept on how to relate this to this, which I will review today. But before we stopped last lecture, we made the observation that if I look at this and I don't exactly specify what L is, this looks superficially almost like a Schrödinger equation, in the sense that I have a quantity that changes in time on the left-hand side, which is associated with some probability. In this case, it is the probability density in phase space. And I have a differential operator that acts linearly on this quantity on the right side. What is linear? It is not L rho everything squared, so the same distribution that enters on the left-hand side also enters on the right-hand side. And this operator contains derivative, which are linear. So this is in fact a linear equation. Okay? So we said, okay, there is some analogy with quantum mechanics here. Well, it's most likely an analogy with imaginary time quantum mechanics, to be honest. Because I don't have any phase here, or any imaginary number I. But other than that, it's a PDE for a distribution that is large dimensional. It has twice as many components as a regular wave function for an n-body system, because a wave function has either position or momentum, not both. Actually, you can build something which is called the Wigner function out of the wave function that has both, but let alone, this is not something we are interested in this course, okay? So, in some sense, we closed the discussion last time to say that determinism of classical mechanics is somewhat overshooting, or if you want, an illusion. Yes, it is there for one particle, or maybe two particles, because the two-body problem is basically one-body problem if you switch the center of mass frame. But as soon as you go to the three-body problem, things get horribly more complicated, and very soon become chaotic. And so basically all of the determinism is gone for practical purposes. You're left with a phase space view, which is not very different from that of quantum mechanics. Okay? Except for all these entanglement, phase, and collapse of wave functions, which are all very, very specific property of quantum mechanics that, of course, don't appear here. There isn't such a thing as uncertainty principle. There isn't such a thing as a collapse of the wave function, Born interpretation, or Copenhagen interpretation of quantum mechanics, and so on. Okay? Okay. I would like you to revisit, if you go back on the notes that I sent you, or if you watch back the lectures over the view, you will be able to trace back how we derived this. And basically everything we did was to apply a total derivative to this, and then use the chain rule. And then when we were using the chain rule, we came up with derivatives of the coordinate, the phase space coordinates with respect to time, which in turn we replaced using Hamilton's equation. So this was done on this particular observable, rho, but there was nothing specific about rho we used. The chain rule is the chain rule for any observable, right? So I think I can convince you that just as much as we did the total derivative of rho with respect to t, and we wrote this as a partial derivative of rho with respect to t plus rho, the Duvillon operator, if you want, negative the Duvillon operator, plus the Duvillon operator applied to rho, remember? we didn't really do that referring specifically to rho. Right? We could have done it for any observable A. Okay? This simple observation will have profound implications where we will try to connect this board where we, actually, the theory board with the experimental board, as we shall see in a moment. Okay? In order to see this connection and to help us build a connection between theory, phase-space distribution, and time averages, it's useful to rewrite the Deville's equation for rho for a moment and then generalize it for everything in a slightly different form. Okay? You follow me? We introduce the so-called Poisson brackets. Let me write it here. Poisson brackets. And the Poisson bracket is basically the right-hand side of the Deville's equation. Is sum over I, d by dq of Ri, d of A, d by dpi of B, negative d by dpi of A, d by dri of B. This is a definition. There's nothing to understand here. It's just a definition. Okay, just copy it down. So with this notation, the Deville's equation becomes d by dt of rho equals negative d by dt equals Poisson bracket of rho with the Hamiltonian, right? Because basically that's what the Poisson bracket do. Now we see a second so if I am slightly more general, I can write d by dt, the total derivative of any observable, as equal to the partial derivative of the observable plus the Poisson bracket of A, h. Where here I'm using the fact that basically the derivation we did for the phase space density was based on the chain rule, but in addition the phase space density could use the Deville theorem that says that the total derivative of rho was 0. Remember that? So for the space density this is actually 0. But for a generic observable A function of the phase space, you have this general mathematical structure, right? It is telling you how in classical mechanics, an observable changes with time if the underlying dynamics is Hamiltonian. Do you follow me? Have you ever seen any equation like that? Kind of similar to that in the past. Huh?
Similar to the
The RFS, or even the RFS theory is already about averages. What you have in mind is the Heisenberg theory, is the Heisenberg equation for the operator, right? Because in quantum mechanics, first of all, in quantum mechanics, observables are associated with operators themselves, right? So now I put a hat here. Correct? Over time, this is partial derivative plus the commutator now. Correct? I find this fantastically elegant. Because it really emphasizes that quantum mechanics and classical mechanics, once you accept the statistical view, are not that dissimilar after all. Yes, again, there is all of this intrinsically quantum entanglement, spin symmetry, degeneracy, Fermi versus Bose statistics, and all of that there has no classical counterpart. When you talk about distinguishable particles, and you give away all of that happens in the moment you make a wave function collapse, and when it comes to evolution of the wave function, there is a strong analogy between it. Okay? So why am I bringing this up? Not because I'm fascinated by the aesthetics, which I am. I mean, as a theoretical physicist at least, I have fell under the spell of the beauty of equations. And this analogy is undoubtedly beautiful. Because it tells you, you want to quantize a system, all you need to do is to replace Poisson bracket with commutators, and you're done. Right? But there's another reason why I'm telling all this. It tells that in quantum mechanics, a conserved quantity follows. So if you forget the explicit dependence of the observable, for instance, what is an explicit dependence? It's a dependence that does not depend on time through the phase space coordinate. For instance, the energy of the system may depend on where the particle is going, but it may also depend on the fact that I am increasing with time the electric field in the room. That has nothing to do with where the particle is. Of course, it will influence the total energy through the coordinate as well, but this is an external dependency, right? So the total derivative depends through the phase space coordinate on time. But the partial derivative is I depend exclusively. So if I let this go in for a moment, an observable quantity is conserved in quantum mechanics if it commutes with the Hamiltonian. And in classical mechanics, if it Poisson commutes with the Hamiltonian. Okay? Okay. With this huge mathematical digression, not huge, but significant mathematical digression, I'm ready to go back to the problem that I mentioned before. How do we connect Poisson, a theoretical approach to an experimental approach? Okay? So, at least in the so-called equilibrium statistical mechanics, which is something we will refer to at the beginning, then we will go into non-equilibrium, but at least within the concept of the equilibrium of statistical mechanics, the matching between theory experiments occurs through what we call the ergodic hypothesis. The ergodic hypothesis means I assume, I postulate that my system basically obeys the zeroth principle of thermodynamics. Meaning that if I leave it alone long enough, it will converge to a stationary distribution, right? Where you can define a temperature in a closed form, right? That's basically the zeroth principle of thermodynamics. So we will assume that this is the case for our system. In practice, this is always the case unless something keeps the system out of equilibrium. For example, if you have a set of protein that burn ATP, you keep on injecting energy through the conversion of chemical energy into the system, and if you do that at a constant rate, you're never able to dissipate that energy and reach equilibrium. You're constantly driven out of equilibrium. It's like keeping something inside a microwave and leaving the microwave open, right? You keep on pumping energy into the system. That's an example of out of equilibrium system. Another example of out of equilibrium system is instead of having water in a glass, you have a bathroom tub in which you pour in water from the source and you get it out from the sink at an equivalent rate. There will always be a current from the sink to the source that will never go away because I'm pumping matter into the system and taking it out. So these are examples where whatever I'm going to say is not applicable. Correct? But for all systems in which you don't fall into this particular category, we can assume the principle zeroth of thermodynamics hold. There is a temperature, there is a stationary distribution. So if there is a stationary distribution, it means that I can find a rho. Yes?
But in the example of water, also that is right to say that is a stationary distribution.
Yes, but you cannot define a temperature. You cannot define a temperature because the mean kinetic energy has a finite mean. The velocities have a finite mean, which is the flux. It's set by the velocity of the fluid. So that's why I specified I have a stationary distribution and I can define temperature. So the mean velocity of the system is zero, basically. Okay? The mean velocity of the atoms in the system are zero. So let's for a moment forget about all these exotic situations and let's worry about them later if needed. We know by we postulate that if we leave whatever is my initial condition in the phase space, I have an initial transient phase in which the phase space distribution changes. But ultimately, I will reach a stationary phase space distribution, which will not depend on rho. Right? Are you with me? This phase space distribution, because of this Poisson bracket description that I just mentioned, the phase space distribution will be such the stationary phase space distribution will be characterized by a particular value of the Poisson bracket. And what is this value? At equilibrium. 0, because this would be negative, the time change of the phase space distribution, right? So, 0. But now remember, now we are learning something. That for a distribution to be stationary, it has to commute with the Hamiltonian in the Poisson bracket sense. It has to have Poisson bracket, the Hamiltonian 0 is not commute. I will use the word commute improperly here. It has to have a 0 Poisson bracket with the Hamiltonian, right? But if he has a zero Poisson bracket with the Hamiltonian, it means, so what are the distributions that have zero Poisson bracket with the Hamiltonian? Well, are the distributions that depends on the phase space variable through functions and f is a conserved quantity. Think about it. The commutation with h implies conservation. If f is a conserved quantity, its own equation will have vanishing Poisson bracket. So you can easily prove, for a moment let me not do that, that the condition of stationarity is obeyed if your distribution rho depends on the phase space variable through conserved quantities. That is, quantities that commute with h in the Poisson bracket sense. Okay. The commutation of any observable with any conserved quantity will not change in time, so it will commute with the Hamiltonian in the Poisson bracket sense. Right? Now, if rho depends on the gamma through a conserved quantity, you're guaranteed that this function rho will commute with h, and so will be stationary. So we are telling you a property of stationary distribution. Stationary distribution can be written as functions of quantities that commute with the Hamiltonian in the Poisson bracket sense. Okay? So, for instance, rho of gamma in a microcanonical situations, say suppose a conserved quantity is energy, okay? Then clearly, energy commutes with the Hamiltonian, right? It is the Hamiltonian, right? So what we know is that in a system that conserves energy, the stationary distribution will depend on the phase space variables only through the conserved quantity, which is energy. So if energy is conserved, say d by dh of t equals 0, because that's h comma h, which is obviously 0, right? Then rho of gamma is in fact a rho of h of gamma. Okay? And in fact, you probably know in the microcanonical setting, this is absolutely true because basically E is the delta function of H, the ergodic surface. But we will worry about determining these probabilities later. We will not now, we will today start this discussion. So let me summarize what we have achieved so far in this lecture. We started off with the problem of connecting theory and experiment. We momentarily put that problem on hold. We looked at theory alone, correct? Theory alone, Liouville's equation, all of that. We recognize conservation laws in classical setting associated with Poisson bracket. We postulated the existence of equilibrium, and now at equilibrium, the stationary distribution depends on the phase variable implicitly as a function of conserved quantities. Okay? You all with me? Now we're ready. We postulate the ergodic assumption. And the ergodic assumption is, if there is such a thing as equilibrium, an infinitely long time average will give me the same result as a phase space average over the stationary distribution. Let me write it. The ergodic hypothesis this is the stationary. And since it's stationary, I have very important information. I know that it will depend only on gamma through conserved quantity. So everything we said about Poisson bracket will tell us some properties of the stationary distribution. The ergodic assumption is independent on that properties because it doesn't ask me to know the structure of rho of gamma. Correct? So, at least from the conceptual perspective, now we have identified one way of connecting theory and experiments at an incredible cost. The connection that we have done so far assumes that you forget about asking any question about the transient. Any questions about dynamics, in other words. That's a huge toll we are paying here. But we will relax this constraint later on in this course. And we must do that because much of what we are interested in has to do with dynamics, especially in biophysics. Protein folding is dynamical, right? Whatever conformational transition is not something that happens, you're not interested in the mean value. Say, for instance, you have a protein that goes from closed to open, and maybe you are exactly at a temperature which you've spent 50% of the time closed and 50% of the time open. The average distance will be somewhere in between. We'll learn nothing about this transition from the average alone, right? So only dealing with equilibrium and forgetting completely about time is not going to give us a lot of information. So why is statistical mechanics, equilibrium statistical mechanics, being so successful? Well, this is mostly because from this formulation then you can recover basically the laws of thermodynamics from connecting them to mechanics in a rigorous form and say, okay, basically I see how basically these very empirical laws of thermodynamics with all these potentials and blah, 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 connect to then underlying mechanics, Newtonian mechanics. So I don't need to add them as an independent theory that lives on their own. Remember, before Boltzmann and Gibbs, people had no idea what the heat was. They thought it was a fluid. They were trying to, now what Boltzmann really did is that forget about adding new physical entities. It's just classical mechanics for many, many degrees of freedom. And here I can show you that I can introduce a free energy, I can introduce entropy, and I can introduce thermodynamic potential starting from a microscopic description, right? So that is certainly a huge advantage of statistical mechanics in equilibrium. And bringing this forward, it has allowed people to study phenomena like critical phenomena where you have magnetization of a system. Now, if you have a magnet at equilibrium, now you're interested in how lowering the temperature things change dramatically, right? For instance, you develop a magnetic field, a magnetization. All of these quantities are of interest, of physical interest, but they don't depend on time. In biophysics, and in general in macromolecular dynamics, we are much more keen to learn about time dependence because most of what we are interested in, especially in biophysics, has to do with things happening, and the very concept of happening involves passage of time. So at some point, the ergodic assumptions alone will not be enough to make predictions that we can actually use. We will have to learn to make predictions in the transient regime. Okay?
I just forget. I got that rho depends on is stationary because it depends on something that is conserved. But why can we say that it is equal to the 500? I didn't get.
No. Okay, no. this connection between the Poisson brackets, conservation laws, and the structure of a stationary distribution tells you some properties of the stationary distribution. It doesn't connect that to the time averages. It just tells you that if there is such a thing as a stationary distribution, it must depend on the phase space variables through conserved quantities. Okay? You follow me? Now, what do I do with this stationary distribution? Well, the ergodic hypothesis states that whatever I compute as average over this phase space variable will give me the same result as making an extremely long time average. And the picture, this is by far a trivial association. This is the genius of Boltzmann, if you want. Why, and Gibbs, what is the physical picture underneath patching together two universes that don't belong to each other? Is that the system in infinite time has the time to explore all the points in configuration space, right? Strictly speaking, infinite time. And if I do that, I can even do that if I say, instead of taking a picture of my system every short time so that the configurations are correlated, so my system was here and then it's slightly displaced, I can do that every long intervals. So much that if I put all of these configurations, I cannot trace a trajectory any longer. They all look like random, right? Say, I take a snapshot, I go, I get a coffee, I take another snapshot, I go, I get another coffee. At the fourth coffee, I cannot sleep anymore, but I have 4 independent snapshots, okay? Now, if I keep on doing this, and I can do that because I have infinite time, I get a collections of configurations distributed in phase space. The ergodic assumption is that basically they are equivalent copies and that these configurations are sampled from the stationary phase space distribution. So basically, if I were to histogram these configurations, the ergodic assumptions would say they will go in the most probable regions of configuration space. So they will draw the stationary phase space distribution. But this is the ergodic hypothesis. I mean, there are theorems and mathematicians and statistical physicists have gone all the rabbit hole. You know what it means to go into the rabbit hole of trying to figure out under which condition this is true, and I will not deal with that. I'm not an expert on that, to be honest with you. As far as this course is concerned, we will assume this is true, and it will base ourselves, like Landau does in his books, if I remember well, basically on physical intuition. A very long trajectory that can go anywhere in configuration space, it will draw a histogram, after all, of uncorrelated quantities. And this histogram will draw a density distribution in phase space that is stationary, right? Well, what distribution can it be? It will be the result of a stationary distribution of the Poisson equation, of the Duville equation. So if I do this long average, it's basically the same thing as if I do the phase space average. This is the back of the mind reasoning, but it's called an hypothesis because I'm not proving this to you. Right now, at least.
In a case where the phase space has like two distinct regions that, like I don't know, there is some like a trajectory in phase space is not filling the phase space, then this does not hold.
You touched the very point. For those who are not here in the room, he was asking, what if the phase space is not topologically connected, basically? If a trajectory cannot go everywhere in phase space. This is called the breaking of ergodicity. It means that the ergodic assumption is not that hypothesis does not hold for this particular system. I'll give you an example. That glass over there, even if you weigh the age of your life or for every relevant time scale you can do experiment of, it will stay vertical. But it's in fact a fluid, so in a very, very long time you will see all possible configurations of this object. But it is stuck there because it's a glass, and the glass has an exponentially diverging relaxation time. So long that it exceeds any relevant time scale. So it's like a gas that will take forever to thermalize. Okay? So now in that case you talk about breaking of ergodicity. Now, did I answer to you?
Yeah.
Okay. But now comes the real question. How do we know if our system is ergodic or not? Beforehand. And the real answer is we don't. We never do, basically, in real life. Let me give you an example. Let's take a simulated macromolecules. The leaves starts from a native state. And then I wait a few minutes, a few seconds, and in the experiment it goes to a denatured state, stays there a few seconds, and then comes back in the native state. I'm assuming folding time of seconds, which is not that unrealistic for many problems. Some of them have milliseconds, but say a reasonable range is between milliseconds and seconds. There are some that take hours to fold. Hours. Okay, so I look at my experiment and I see one state and another state, and I see an interconversion of this. For example, I measure the endpoint distance between two probes, two fluorescent probes, and I see a signal suddenly opening up and closing up, changing the frequency of fret exchange, for instance, telling me that the Dyson donor have gone to different distance. Okay? Okay, I see many interconversions, say, okay, I'm in equilibrium because I see it goes from back to forth, back to forth. But this doesn't tell me that if I waited 10 years, the system could eventually find the third state, so much more stable, and stay there for the age of the universe. I have no way to know it. So any statement about equilibrium, any in real life, is in fact a statement about local equilibrium. So in an analogy, and I hope I make sense with this analogy to you, we are like people hunting for the highest mountain. So we start from here, we look around, we go to Resegone, north of Lake Como, we look around, we see probably Monte Rosa, we go to Monte Rosa, we look around, we see Mont Blanc. Who's going to tell us there is Caucasus Mountains and then later on Himalayas? Right? But if we were searching and searching and searching, and maybe the more we search, the farther we look, which is not what happens to observers, but we build batteries. We eventually build some telescope which uses whatever satellites and discover, hey, there's Himalayas over there. But we never know. So any statement about equilibrium is in fact a statement about local equilibrium. And this happens both in simulations and in experiments. But it's much more severe for simulations because typically experiments can last for times that are very long compared to the molecular time. Say, it's not a problem for you to do an experiment that lasts minutes, which is a gigantic time for the macromolecular time scale. But you can never simulate minutes of molecular dynamics. I told you the most powerful special purpose supercomputer go to the many milliseconds, and that's an incredible achievement. Normally with conventional supercomputers, so it's conventional but supercomputers, you scratch, say, tens or hundreds of microseconds if you really invest significant money and CO2 emission into that calculation. Let's not forget, a very extensive calculation can easily cost you hundreds of thousands of euros, millions even. okay? And CO2 emission, consequently. So it's much more likely that we stumble into the question, is this really ergodic or not, when we do simulations, than we do so when we deal with experiments, with noticeable exceptions. You know prion diseases, right? You know what is a prion disease. A prion disease is a disease that occurs when a protein called the prion protein changes shape when getting close to a template of misfolded. It's a misfolding disease. You have stays in the native state. We all assume it's the lowest energy state and that its thermodynamic oscillates between stable and unfolded states. But if this prion protein gets close to a template of misfolded protein, it would be likely to interconvert into a misfolded protein and to aggregate into this aggregate of misfolded proteins called prions, which are invariably lethal for humans. Now, this is a new state, thermodynamic state, that has even lower energy. So once the protein gets into that new state, it never converts back because the barrier to come back is huge. So you believed you were in equilibrium, but then when you have this extra system here, when it gets closer, you discover there is another state. And that is really the minimum of free energy, and it's so deep minimum that you will never be able to see a return from that. That's a break of ergodicity. But the break of ergodicity is at the scale you look at it. Maybe if I waited 3 times the age of the universe, I might see a spontaneous breaking of a prion into its prion protein components. It doesn't happen, okay? In any relevant time scale. Is this discussion sort of making sense to you? Very good. So we did a long way, but now we are left with the very important practical question. How do we get these damn stationary distributions? If we ever want to do something, we need to be able to do 2 things. Thing number 1, know what are these distributions. Thing number 2, being able to sample from this distribution on a computer. Forget about doing things by hand in this field, right? There's no way you can do things without a computer for macromolecular systems. So we are left with these 2 fundamental challenges, and that's what we're going to touch before we take a break, and then we start doing some simulations. You will start doing some simulations where we'll apply all of these concepts. So before we arrive to that first milestone of this course, we need to answer these 2 fundamental questions. How do I know what is the functional form of these stationary distributions? Why do I use the plural? Because you have a different stationary distribution depending on what is your conserved quantity, right? Because remember, I only told you that if you have a conserved quantity, the stationary distribution will depend on the conserved quantity, on the phase space variable through the conserved quantities. For instance, you might conserve energy, or you might conserve the number of particles and the average kinetic energy, right? So you might have different constraints, right? So different constraints or different conservations will imply different ensembles. Ensemble is a set of statistical objects and a distribution. So we will need to compute the distribution for the different ensembles that are relevant for simulations. Second task, we will need a closed algorithm to sample those. Okay? So, what time is it? 20 minutes. Okay, so I could say the topic of this lecture ends here, and I have an extra 20 minutes, which I will not lose, I will use. But you might consider this next 20 minutes as a premise to the next lecture. Okay? And we will retake these discussions, but we will go, next time we will go straight to the point. This time we go slowly and we make some step to get closer and closer using our brain, rather than me driving down the derivation. Okay, so the question that I will address is how to compute the stationary distributions. Okay? The traditional way to do that is the Boltzmann-Gibbs way to do that. Start with the macrocanonical ensemble. In macrocanonical ensemble, you know the energy, and you can infer that the distribution is basically uniform at fixed energy, which is the microcanonical distribution. Then you do the canonical distribution, you put in the heat bath, and then making small changes of energy. I'm not telling you this as you should know it. It's just try to touch on something you might have remembered from your past education. Okay? Have you done the canonical ensemble derivation at some point in your life? That's the way the Boltzmann, Gibbs, and company have done it. In this course, we'll take a different route. And we'll take a different route for two reasons. First, because you have already taken that route. But most importantly, because it teaches something. It's a different perspective. It yields the same results but in an entirely different mind frame, which is useful both for connecting with information theory, and therefore informatics, and therefore algorithms, and therefore machine learning and stuff. And also because it teaches something fundamental. And basically, the topic of this derivation is information theory derivation of the ensembles stationary distribution. Is it clear what we, in the second part of the sentence, derivation of the ensemble stationary distribution means? What I don't think it's clear to you is what the hell means information theory at this stage, unless you've seen it already, of course. Have you seen this already? Shannon's entropy? No, fantastic. I mean, to me, when I saw this first, it was a little bit like the first time I saw a relativistic transformation, and some corner of your brain, of your mind sort of opens up, and you start thinking in a way that you weren't thinking before. So that's profound. You know, when you first see that time and space are relative, and the concept of things happening at the same time, it's only frame dependent, your mind is no longer the same, right? Something is irreversibly changed in your mind. And maybe with a little bit of exaggeration, I think the same thing happens when you think about information theory. So in 1948, I think, I want to put some... Among other things, people were developing computers, right? And computers, people have already understood that the concept of bit was at the core of digital computing, so binaries. But of course the technology was horrible. And if you were trying to transfer some bits by current states, all sorts of noise would happen. And so your message was subject to noise. The situation was not very different from what is the situation of super modern computer today when you talk about quantum computers. People are very excited about the idea of a quantum computer. Problem, the qubits, the quantum bits are extremely noisy, and you have all this problem that noise destroys the calculation, basically. Now, in quantum mechanics, it does that by destroying even the quantum nature of the entanglement. In classical computer, we're just changing the flips, flipping zeros into ones. So a fundamental question that Shannon was interested in addressing was, how much information do I lose? How much information do I have in a sample? And since, again, they have this problem that the bits were fluctuating, he had this, it was already routed at the time that they had distributions over bits. That it could be, the probability to find a bit 0, 1 was not deterministic, okay? Now, enough for informatics. This is just the background. We don't need that. But Shannon started to think, how do I define information in a rigorous sense? He came across with this genius idea that this information is related to the concept of surprise. So, when if I have a statistical ensemble, and I have an idea of the distribution, I make a measurement, and after making the measurement, I have a completely different picture. For instance, an unlikely event occurs, something that goes far beyond my prior knowledge. I'm using Bayesian terms here. I don't know if you have some backgrounds. So if I have a prior distribution, but then the posterior is completely different, I have a surprise, right? So the distribution that carries the least information is the one that will be most surprised, if you want. Right? Because anytime I make a new measurement, I start knowing something about the distribution. So here comes the question. What can I say about a distribution that contains the minimal amount of information, other than some constraints that I decide to fix? What does the hell that mean? Well, let me rephrase it in a form that you might feel more familiar with. What is the most unbiased choice for a distribution I can make? That only takes into account of whatever the distribution really knows for sure, the constraints, and nothing else. Okay? Whatever else, so in other words, if you want, I have a prior distribution that is as agnostic as possible. Okay? Well, if I have a distribution and I have a set of constraints, for example, I want to keep the temperature fixed, the expectation value of the energy or whatever, right? Have a temperature fixed. What is the most unbiased choice of the stationary distribution? And I can guess a distribution. Maybe I say e to the negative, well, something squared b h squared. H is the Hamiltonian. Why not? It depends on something that commutes Poisson-wise with the Hamiltonian, right? So this is a perfectly legit guess. Is it unbiased? Of course not. I made it up. Maybe h to the 4 is better. But I don't know because I guessed h to the square. How much information am I putting down by guessing a function of 4? That's my prior, and I might not be even aware that I'm putting this prior in. Right? Okay. And here comes the genius. Statistical mechanics, which we will stand upon this rigorously, at the same time offer the answers to the question in a kind of a loop. I'm going to tell you what I mean. So in order to give you the answer, let me ask you a question. Suppose I give you 4 cards. I'll say 5 cards, whatever, n cards, but I would say 5 because I can put it on the board. And each card can be either 0 or 1. For simplicity, I could use all different cups, clubs, hearts, diamonds, and whatever, right? But I'm not going to do that for sake of simplicity. Now I'm gonna show you 2 different drafts of cards, right? So player number 1 gets this. Let's say there's 6. Okay? Player number 2 gets this. What's the difference between these 2? No difference, right? Yeah. What about this and this? I just swapped around the 1s and 0s. No difference, right? Okay, what about this? Again, no difference. What do we mean by no difference? Since every number can be 0, 1, the probability of this is 1 of, I'm randomly giving you these cards, and you will get 1 half, 1 half, 1 half, 1 half, 1 half, 1 half, so 1 half to the 6th, and this is one combination out of 2 to the 6 possibilities, right? What about this? What is the probability of this? This very one. Huh? Is it bigger than this? It's exactly the same. Yet, if I tell you this, which is typically the equivalent of getting the Scala Reale in poker, or the poker, something that pays a lot of money, you pay a lot of money for this. And why do you pay a lot of money? Because it's rare. Because if you win every time you get a draft, there would be no poker, right? The fact that you win in poker with a poker is that it's very difficult that you get a poker, right? That's the very essence of betting, right? So why this is worth more than any of these if they have the same probability? You already mentioned the name. Before calling the name. Huh? Yeah, because there are endless of this. But this is different, not in its own probability, but because there's some particular ordering, and there's very few ways of order them. In this case, there's only one way to order all the 1s on the left and all the 0s on the right, but there are, I could count them combinatorially, let me not do it, endless way of doing everything else, right? So basically it's the total number of combination minus that one, essentially, right? So although the individual events are equally likely, this stands apart because there's only few of them. Okay, and when I was asking you what is the difference, you came across, so clearly this is less unbiased than this. If I tell you, give me an unbiased set of card draft or die draft, you would not come up with this, right? You would intuitively, I'm building intuition here, not building theorems here, just preparing the lecture, okay? So if you feel confused, it's not because you should be understanding, it's because I'm bringing you there by thinking, and then we formalize. And you will always have to remember the formalization if you want to, but I want you to think, not only just to remember the steps, okay? So you will not be drawn to say, oh, that's my unbiased set of 0s and 1s. You would probably come up with one of those, one of the gazillions of those, right? And somebody in the audience, Federico specifically, came up with the idea, oh, this has to do with entropy. But really, we don't know what entropy is when we got to the thermodynamics course, because entropy in the thermodynamics course, remember, is whatever is the integral of dq over t for fixed t reversible curves. Remember that incredibly obscure quantities which I remember well, it was like dq over t on a reversible path. What the hell is that, right? And then people mumble jungle that it has to do with the reversibility. Why? Because we know that when we try to compute, when we state the two Carnot and whatever, I never remember, Kelvin statements of the second principle of thermodynamics, they tell us something that doesn't happen. And we then connect the fact that something doesn't happen because this has to grow in the universe, right? I see no connection with probabilities, nothing. It's just hardcore engineers thermodynamics. And I stress engineers because this was done by engineers. They had to build, in the Industrial Revolution, they had to understand how much work you could get out of machines. They couldn't care less about what was underneath. Maybe they cared. Here came Boltzmann that, took it so seriously that eventually committed suicide because it was stays. And actually, a student who actually took over his challenge also stumbled and eventually committed suicide. So there's a famous book in statistical mechanics. In the introduction says, okay, now you're studying statistical mechanics. The first one who tried to solve it committed suicide. The second one committed suicide. Now it's up to you. What are you going to do? So it's kind of depressing. But yes, so Boltzmann and took his fundamental question very seriously. What the hell is entropy? And then he understood that entropy has to do with the number of equivalent states. And he came up with the idea of relating entropy to number of states. And then came Gibbs, who said, okay, if I have a distribution over some coordinates x in general, I call the entropy negative of a constant that he named after Boltzmann, the average over my distribution of the logarithm of the distribution with a negative sign. So this is a measure of the number of this grows linearly with the number of equivalent configurations, right? So this is how the connection between this and this takes place through the Gibbs formula, okay? I don't want to redo this for you. But what I want to say is that in here is the idea that the systems naturally converge towards the most disordered distribution, which is the second principle of thermodynamics, right? What does it mean, disordered distribution? It means a state in which you have many identical copies rather than one. For instance, I give you a brand new pack of cards. They are all nicely ordered, and then you want to mix them. And hell, after you mix for a while, you get one of the disordered states. The probability that you mix, you look and you find back the original state, if a fair pack is provided to you, is basically zero, right? So anytime you sort of act on the system spontaneously evolves towards a more disordered state. So this evolution, because you see the problem is that you want to see something that changes, but energy doesn't change. Right? For instance, on Earth, all the energy that is provided by the sun is radiated away. Right? Otherwise, we would have boiled like Venus millions of years ago, right? So it's not the energy of the Earth that changes. So what is supporting life? Well, energy. But what's going on? So energy doesn't go away, but we went from the primordial soup to whatever your best actor or actress is in terms of being nicely ordered. Okay? Clearly, we went from a disordered state to a very beautiful ordered state, right? So something must have changed. What has changed? The number of beautiful states compared to the number of soup states, right? There's only one Brad Pitt in the world, okay? Or take a female actress if you want for gender equality, okay? Which means we are going opposite to this drift toward more disordered states. Why? Because we're using the energy of the sun. and if I counted how much disordered states there are now in the sun after it burned all its helium over these million years, it overcompensates the reduction of entropy on Earth. So that overall, we went to a more informative state if I count the Earth and the sun. Remember this discussion, right, from your thermodynamics course. All this to say that we have now a guiding principle to understand what is the most unbiased state. It's the most entropic state, right? Because the system naturally evolved towards states where you're more and more unbiased. So, this brought Mr. Shannon to formulate the idea that became famous as the maximum entropy principle, even for contexts where statistical mechanics has nothing to do with it. He postulated that if I have a set of events described by a discrete set of probabilities, probability of event 1 is 1, P1, probability of event 2 is P2. For instance, the probability might be the probability of drafting a particular type of card from your pack, okay? And then suppose that this system is subject to a certain constraint. For instance, there are so many club cards, or there are whatever constraint you want to put, okay? Then the most unbiased distribution that you can get will be one that maximizes function pi log pi subject to the constraints. Do you follow me? As a general idea. We will not formalize this. This is a principle. It's called maximum entropy principle. This is called the information entropy because it tells you how much information is in a given distribution. Remember, the most uninformative information you expect to be the flat distribution, for instance, if you know nothing else other than it's a distribution, right? Anything that is not flat contains information. There's more probability here than there is there, right? So the most unbiased distribution is one that maximizes the entropy given the constraints. And it's a principle. You can write it down. You don't have to question it. You don't have to prove it. Either you believe it or not. It's a principle. Okay? And we will follow this principle because it will give us good results. When is a principle accepted? When you make predictions that are verified. If you use a principle that gives you wrong prediction, then it's not a good principle, right? So the first thing we will do tomorrow, because unfortunately we run out of time now, is to check the very least. If I know nothing about distribution, about the distribution, what is the most likely, most unbiased guess for that distribution? Well, it's one in which all events are equally probable, because I have no reason to favor one event. If you want, for the principle of insufficient reason, which is sweeping the dirt under the carpet, as you can see, replacing one principle by another, but you get the point, right? So if we maximize this entropy for any particular choice of decay, will we get a uniform distribution? That's a very reasonable question. And tomorrow we show that this is indeed the case. And once you've done that, then we say, aha, we will follow James, who followed up Shannon 10 years later and say, okay, but then I have a way to construct all ensembles I want. I want the most unbiased stationary density matrix compatible with the constraints of having fixed energy, compared to the constraints of having fixed average energy, compared to the constraints of having fixed pressure. So basically what you do, you maximize the entropy with constraints, and I expect you know the Lagrange multiplier formalism. Do you know what it is? To add constraints. We will review it tomorrow. So we use this mathematical idea of minimizing with constraints, and you will get the microcanonical, the canonical, the grand canonical, the MPT ensembles, and all the ensembles you want. And now finally we see the connection, right? Between what we started off, getting the stationary distributions, because we want to make contact with experiments, so we want to use the ergodic hypothesis. And now to make this practical, we need to compute those distributions with this detour on the Shannon entropy detour to get those distributions. Okay? Fine.